Hi, minasan, konnichiwa, Zamurai Engineer desu. So in this live stream segment, we will have the rectangular beam design, and after that, we will have the one-way slab design. Okay. So here, it is somewhat different and somewhat related to the previous modules and previous live stream discussion, because this is now in particular design. This is a way to give you the procedure how to do the design. Okay. So previously we do the actual analysis of the beam. That is the analysis portion. So now we are designing. And the difference that although we are using the same concept, we are using the same code, we are using the same formulas, the same tables, the same given, or the same principle, we will do it in the reverse order. So when we are doing the analysis, we are given the dimension, we are given the areas, or we can at least find the areas. But now, we are not given the dimension, we are not given the areas. We are going to determine it through the design process. We are going to determine the size of the steel bars. We are going to determine the size of the concrete beam given the nominal moment or the design capacity. So we will do it in reverse again. So this is your professor, Dr. AP. I would like to wait for the confirmation on our sound check. Okay, thank you, Mark Leo, for confirmation. Shout out to Mark. So therefore, since our sound check is okay, let us proceed with our discussion. So our next or the initial section is about load factors. So load factors, we already have the same discussion about this, and if you can notice, we are going to memorize the same 7 formula as we had in steel. These are given in steel design, but the same in reinforced concrete design. The same 7 formula. This is on the part of strength design or LRFD. So strength design is what is this called in reinforced concrete. If you are talking of steel design, this is called LRFD. Okay. So if you are talking of reinforced concrete, this is what we call ultimate strength design. Okay. Are we clear? So we have what? Dead load, live load, and design or ultimate load. The structure needs to be able to resist. Okay. So we have the U, we have D, we have live load. Well, we have LR. LR meaning roof load. S is snow. R is rain load. W is wind. What else? E meaning earthquake. Okay. So those are the same on the previous discussion. So we don't need to take up so much time about that. So let us similar to our steel design, we have an example. So let us again do this example for the benefit of having repetitive example. But our previous example is under the steel design. So we have in the reinforced concrete example of corresponding determination of critical design load. Okay, you're using load combination. Okay, so we have given what? Gravity axial loads for a building column estimated with the following: dead load 150 kips, live load from roof, that is LR, 60 kips, and live loads from floors, L is equal to 300 kips. Wind compression, okay, compression wind, that is different from tension wind. So the difference is the direction. They are opposite from each other. So tension wind is 96 kips. Compression wind is 112 kips. Okay. Seismic compression 50 kips. Tensile seismic 40 kips. Okay. So therefore, determine the critical design load using load combination. Solution. Okay. Number 1 formula, dead load alone, that is 1.4 D. So therefore, 1.4 times 150, that is 210. Okay. Formula number 2, using formula number 2, dead load times 1.2 plus 1.6 times live load plus 0.5 times roof load or snow load or rain load. So there are no snow load, there are no rain load, therefore roof load. Okay, so 1.2 times 150 plus 1.6 times 300 plus 0.5 times 60. That would be equal to 690. How about equation number 3? Equation number 3, that is 1.2 dead load plus 1.6 roof load plus 1 times live load or 0.5 times wind load. Okay. So initially, we have to use live load here. So times 1 times live load. So therefore, 1 times 300. Okay. Dead load times 1.2. Roof load times 1.6. That is equal to 576 kips. Okay. Next, using in this case using the compressive wind. Okay. Okay. Compression wind is 112. Okay. While the tensile wind is 96. So let us do that. So live load 1.2 times 150 plus 1.6 times 60. So this 60 is roof load times 0.5 times 70. Okay, there is a what? Error. There is no given 70. There is an error. There is no given 70 here. Okay. Okay. So this is supposed to be compression wind, which is 112. Okay. So there is a typo error. Okay. So instead of 70, please correct this part. Please correct. This is 112. That refers to this one. Okay. That refers to this part. This part only. This part. Okay. So that is not 70. There is no 70. What about the next one? negative 60. There is no negative 60. There is 60, but there is no negative 60. This is the 60, that is roof load. But there is no negative 60 or tensile wind. There is no tensile wind. Tensile wind meaning you are being pulled. Okay? Compression wind meaning you are being pushed by the wind. The wind is going after you. Okay? So, please confirm what is the value, correct value for this. Please correct it. These two are wrong. Okay? So, equation number 4, 1.2 times dead load plus 1 times wind load plus 1 times live load plus 0.5 times roof load. So, therefore, 1.2 times 150, 1 times, there is no 70. There is no given 70. This is wrong. Okay. Wind load is 112. So, apparently, the given value for wind load then different. Okay. So, what about earthquake load? So the given value for earthquake load is 50 and 40. Can we check it? 50, okay. 50 is compression. 40 is tension. That's why it is negative. Okay. So therefore correct. So this is the correct value. So again, wind, this is wrong. That is wrong again. This is also wrong. Typo error. And then these are correct. So this equation 9.6 A and 9.6B, 9.4A, 9.4B, and 9.3B, 9.3C. Those are wrong. So there are 6 answers that are wrong. And after finding all the answer correctly, please confirm your answer. Use your calculator, please. Okay. Find the answer. After finding the answer, you have to compare all the values. Which one has the highest value in all of this? Which one? So 1, 2, 3, 4 times 2, 5, 6 times 2. So there are 13. There are 13 answers. So compare the 13 result. So the highest is 690. So therefore, that is our answer. Okay, that is the critical design load, 690 from case 9.2, equation 9.2. Okay, so that is our 4.1. So let us go to the next, design of rectangular beams. So we need beam proportion. Okay, so the proportion of D to B is within 1.5 to 2. Okay, the proportion meaning, okay, D is greater than B. D is greater than B, and as the proportion, if you have the value of B, you can multiply by 1.5 or 2. Okay? That is the beam proportion. What about the next? Deflection. Okay? Okay. Deflection, we can use this table. So we can use the table L over 20. So Please use this table for deflection. Okay? Minimum thickness. Okay? So, for simply supported beam, L over 20. For solid one-way slab, for beam or rib one-way slab, L over 16. Okay? So, that's why we will what? Do the design of one-way slab and beam, because we have the same table. So this is for solid one-way slab, and beam is equivalent to rib one-way slab. Okay, we can also do this. Okay. So for rib and beam, L over 16 for simply supported. Next one is one end continuous. Next is both end continuous, then cantilever. So meaning to say, you have to do the cantilever first. Okay, this is how you immediately recall this table. Cantilever for beam 1 over 8 or L over 8. Okay, cantilever. What is the next sample of cantilever of beam? Simply supported. So L over 8 multiplied by 2, L over 16. Okay? And then you are going to one end continuous plus 2.5. So 16 plus 2.5, 18.5. And then 18.5 plus 2.5, 21. So L over 21. So it is easy. So L over 8 times 2, 16. Plus 2.5 and then plus 2.5. Okay? On the other hand, if you are going to design the solid slab, start with cantilever 1 over 10 times 2, 1 over 20 plus 4, 1 over 24 plus 4, 1 over 20. So you can immediately memorize this table. Okay? Are we good? Are we good? So we need this table in order to find the thickness h, the value of h. Because we are given the load, therefore we want to design the dimension and the reinforcement or area of the reinforcement. So number 3, estimated beam weight. Okay, estimated beam weight. The weight of a beam to be selected must be included in the calculation. Okay, so the weight estimate for the beam selected in this text are generally very close because the authors are able to perform a little preliminary paperwork before making their estimate. So, because why do we need to have the beam weight? Initially, we have to estimate. Why? Because we don't have the dimension. How can you estimate the weight if the element do not have dimension? Do not have dimension. There is no H, there is no B, there is no D. How can you estimate the weight? There's no dimension. We can find the weight if we are given the dimension. So we need first to estimate the beam dimension. First estimate, initial estimate. Okay. So how the author do that? Okay. Following the same procedure as did the authors, however, you can do a little figuring on the side and make a very reasonable estimate. How? So from this, for instance, you could calculate the moment due to the external loads only. Select a beam size and calculate its weight. From this beam size, you should be able to make a very good estimate of the weight of the final beam section. So first, for initial guess, initial estimate of the weight from what? Due to external load only, because the weight of the beam is also must be included as the load. Self weight is a load. self-weight is actually a dead load. So self-weight must be computed. So you have the initial estimate external load only, not including the self-weight. Okay? So another method for this is to estimate beam sizes is to assume a minimum overall depth edge equal to minimum depth specified by table 4.1, table 9.5 if deflection are not to be calculated. The minimum for the beam in question may be determined by referring to table 4.1. So the beam width can be roughly estimated equal to about 1/2 of the assumed value of h, and the weight of this estimated beam calculated BH over 144 times the concrete weight per cubic foot. Okay, so you can immediately have a quick and dirty calculation of self-weight. Okay, so just multiply BH times the per unit weight of the concrete. Okay, so per unit weight of concrete, that is 23.6 kilonewton per cubic meter. Okay, so after MU is determined, okay, what is MU? MU is the design strength. Okay, is determined for all the loads including the estimated beam weight. The section is selected. So we have to repeat the process if the initial is not acceptable. Okay, if the dimension of the section are significantly different from those initially assumed, it would be necessary to recalculate again. Repeat. What's a significant change? Okay, you must realize that we are not interested academically in how close our estimated weight is to the final weight, but rather we are extremely interested. So, again, this is the difference of mathematics and engineering here. Okay? We are not interested. The author said, okay, we are not interested academically. Okay? But rather, we are extremely interested in how close our calculated MU is to the actual MU. In other words, our estimated weight may be considerably in error, but if it doesn't affect MU by more than, say, 1% or 1.5%, okay, so you don't need to recalculate. You don't need to recalculate if that is within 1 or 1.5%. Okay? In example 4.2, okay, so we'll do that. In example 4.3, so we will have another example and up to example 4.4. So the authors have selected the beam whose weight is unknown. Without a doubt, many students initially have a little difficulty understanding how to make the reasonable number estimate. Okay, so we dream up a beam weight estimated out of the blue equal to, so 400 pounds per feet if we are using English unit. Okay, so and so on. Number 4, selection of bars. So we can easily do this. Okay, selection of bars. Okay, we will show you. And then next is the selection of concrete cover. So this concrete cover, usually 3 inches on the previous example, okay, but that is not always that 3 inches, okay, it may be less than, okay. To do this concrete cover computation, reinforcing is located at certain minimum distances from the surface of the concrete so that a protected layer of concrete called cover is provided. So again and again, I several times explained about this. Okay. So specified cover is given for reinforcing bar under different conditions. So we have the values for beam, columns, and slab. Also for cast and place member. For precast or pre-stressed, for member exposed to earth, weather, and not so exposed and so on. So we have different values, sometimes already tabulated values about that. Okay. So minimum edge distance. So minimum edge distance using this. Okay. So minimum edge distance, as you can see. So the clear cover plus 3/8. Okay. So we have stirrups, number 3. Number 3 stirrups here. So this is what we call stirrup. This is an stirrup. So the black dots, those are the reinforcement. So these 2 dots above, so that those are top reinforcement. Bottom reinforcement. Okay, these bottom reinforcement are also called tension reinforcement. These are compression reinforcement. So this steel bar is what we call stirrup. Okay, that is what we call stirrup. So this is how to compute the clear cover. Clear cover, you have to determine the center of the edge reinforcement up to the edge of the concrete. So also clear cover is 1.5. Okay. So if 1.5, so you have to add the diameter of the stirrup plus the radius of the tension reinforcement. Okay? So you can always determine that, compute that arithmetically. So using arithmetic. Okay. So what do you mean by DS? Stirrup diameter. So stirrup diameter in our country, that is usually number 10 or number 8. So usually number 10. Number 10 steel bars or 10 mm steel bars. That is for stirrup. Okay? Usual. So sometimes number 8, but number 8 is not allowed anymore, but I still see construction using number 8 as stirrup. Okay? So the minimum value in the code is number 10. Okay? So then this is how to determine minimum edge distance. Okay? So computation, that is. So we are computing the concrete cover. That is not guess. Okay? That is not wild guess. There is an actual computation. Okay? Minimum spacing of bars also states that the clear distance between parallel bars cannot be less than 1 inch. Okay? Cannot be less than 1 inch or less than the nominal bar diameter. So that is the minimum. Okay? If the bars are placed in more than one layer, those in the upper layers are required to be placed directly over the ones in the lower layers. We cannot stagger the reinforcement. Why? Because of the gravel. Okay? So if we stagger the reinforcement, so the gravel may have difficulty going into the spaces in between the reinforcement. So it may what? It may create vacuum and may create what? Honeycomb. Okay? May create honeycomb. That's why we need to have the minimum spacing and have the placement of upper layers of reinforcement on the same vertical line of the lower reinforcement. Okay, so you can use this one. This is spacer. So sometimes we are using concrete spacer. Okay, but here this is what we call chair. Okay, this is what we call chair. Metal chair. This is what we call metal chair. So instead of concrete spacer, okay, usually we are using spacer here, but now it is metal chair. And usually in our country, instead of concrete spacer or metal chair, we are using stone or gravel. So we are using stone there. So as a spacer. Okay. So let us some example computation here. Computing the minimum beam width, okay, from the cover, spacing and so on. Okay, so that's how we need to what? We need to determine how many units of how many pieces of reinforcing bars we need, because we have a problem of spacing. We have a problem of spacing, so we need to have an idea of how to place the reinforcement. Okay. So let's just talk about this example before we take a break. Example, beam design. Okay. So we are given the following: FC prime 4000, FY 60 KSI, and then we have the beam 22 feet span. So 22 feet span. So simple support with dead load of 1K per feet, not including the beam weight, and a live load of 2K per feet. Okay. So let us assume the value of H. So assume the value of B. So we have the minimum value of this for column, but for beam, so let us say what? H 27. Okay? Let us say 27. So therefore, that is what? 0.1 times 22 feet. Okay? So 10% of the span. So that is the assume. That is how you assume. Okay? That is how you assume. Okay? 10% of the span. Span is 22. So therefore, 2.2. So 2.2 is about 27. So therefore, we have D is equal to about 24. Or here, 24.5. So if you can use 1/2 H as equal to B, therefore B is about 14. Okay? So therefore, we can immediately find out the shelf weight of the beam. If that is the case, the shelf weight of the beam is what? So 14 by 27 times 150. 150 pounds per cubic foot. That is the density of the beam in English units. So in SI unit, that is 23.6. Okay. Divide by 144. This is just conversion factor from feet to inches. Okay, so conversion lang yan. So that is about this value. Okay, so we have the weight. Add this weight, this self-weight to the dead load. So the dead load is 1. So add this. So therefore, the dead load must be 1.394. Okay. So therefore, as you can see here, dead load is 1.394. So dead load times 1.2 and live load times 1.6. There are no other loads. So dead load and live load. So we are going to use equation number 2. So this is the equation number 2. The value would be 4.873. So that is WU. For simple beam, that is WU L squared over 8. So substitute WU, then substitute L to be 22 feet. Therefore, we can find out the MU. Okay, the design strength is 294.8. Assuming 0.9. Also, there are plenty of assumption. We assume H, we assume D, we assume B, we assume phi. So, compute rho. Okay, so computing the rho with the same formula. Notice we are using the same formula. We are just using the same formula. Okay, so here. And what is Rn? Take note of the value of Rn. So let us memorize the value of Rn. Rn is what? Rn is equal to Mu over 5BD squared. Okay, that is the value of Rn. Okay, so nominal resistance. Okay. So after that, you have to substitute Rn to this. Okay, to this. Substitute. So substituting that, so you can find out the rho. Our rho is 0.00842. Okay. So, and that is greater than the minimum. Okay, that is greater than the minimum. So therefore, it could be used. Okay, it could be used, and therefore, we can select the reinforcement. Rho BD, because we have the assumed value of B and D. So multiply those with rho. So we have the value for area of reinforcement. So this area, we can use 3 rather than 2.89. So 3. So 3 number 9 bars. That is. Okay, our answer. So check. Let us check the solution. Okay. So checking this width. Check the width. 14. Is the width of 14 able to carry 3 bars with proper spacing? Okay. Is that possible? So if we are using number 7 bars or smaller bars, minimum width of 12.8 inches would be required. Okay. So since we are using number 9, the minimum width is 9.8 inch for interior exposure for 3. So minimum. So that is okay. So our assumption 14 is okay because the minimum is 9.8. Okay, 14 is okay. Okay, the next. Either choice would be acceptable since the beam width of 14 inches exceeds either requirement. If we had selected the beam width of 12, in the process we might have been limited to the larger number 9 bars because of this minimum beam width requirement. Check our solution. So minimum is less than our computed value. That is okay. What about maximum? 0.0181. So also less than maximum. So therefore, the section is ductile. And our choice of phi is 0.9 is correct. So we are able to prove that our assumption for 0.9 is correct. A. Find out the value of A. Do the same thing in the previous module. How to find it. And therefore, we can find the value 305. And therefore, 305 is what? Must be less than the MU. So our calculated MU is how much? Calculated MU is, how much that? 294.8. So 294.8. So the calculated MU is 294.8, which is less than our capacity of the beam. Therefore, this is okay. This design is okay. So this is our design. So we determine 27, we determine 24.5, we determine cover, we determine all the dimension. So this is the final answer. Okay? Any question? So any question? So that is our example. So with this, we will take a break and return after 30 minutes so that we can proceed with the next live stream discussion and lecture. Okay? So this process is okay when you are going to determine or design a beam and also design a slab, a one-way slab. Okay? So again, there are no questions. Therefore, see you on the next live stream after 30 minutes break. This is your Professor, Dr. AP, preaching engineering for nation.